Welcome back to QHSE Talks, and welcome to our new series, Major Accident Investigations. Today, we're starting with a refinery accident that shook an entire community, rattled the industry, and exposed some of the deepest vulnerabilities in process safety management, the 2015 explosion at the ExxonMobil Torrance Refinery. This wasn't a flare burn-off. It wasn't a small upset. It was an explosion so violent it registered as a 1.7 magnitude earthquake, blasted open a massive pollution control device, and sent an 80,000-pound chunk of steel flying across the refinery, landing just steps away from tanks containing tens of thousands of pounds of modified hydrofluoric acid. And here's the truth that investigators kept repeating afterward. If that debris had landed just a little differently, we might be discussing one of the worst chemical disasters in U.S. history. But the real story of Torrance isn't the explosion itself. It's the sequence, the slow, silent accumulation of unnoticed risks, eroded hardware, reused deviations, and decisions made under pressure. It's the way multiple safeguards, each one supposedly independent, failed together at the exact wrong moment. And it's how hydrocarbons found their way into a part of the system where they should never, ever be.
Okay, so to start, you really need to understand the heart of this whole operation.
Yeah.
The fluid catalytic cracking unit. It's this massive, sprawling piece of equipment, and its whole purpose is producing gasoline from heavy crude oil.
And for what we're talking about today, you can really think of the FCC as having two essential halves, two sides that under absolutely no circumstances are ever supposed to meet.
We call them the hydrocarbon side and the air side.
Okay, so the hydrocarbon side, that's the reactor, the main distillation column. It's where the actual cracking of molecules happens, creating these highly, highly flammable vapors.
And then you have the air side, that's the regenerator, where the spent catalyst gets cleaned up with high heat and a lot of air, and then the flue gas system, which, cleans up the exhaust.
And the number one non-negotiable rule of safe operation is keeping these two sides separate.
Because if those highly flammable hydrocarbon vapors cross over and mix with all that air,
you have all the ingredients for a massive explosion.
Precisely. And the ignition point for that explosion was the very last piece of equipment on the air side, a device called the Electrostatic Precipitator, or ESP.
Let's unpack that, the ESP, because its normal function is just so key to understanding why this was guaranteed to happen once the leak started. It's actually a pollution control device.
It is. Its whole job is to remove these tiny microscopic catalyst particles for the combustion gases before they get released into the atmosphere, to meet air quality rules.
But the way it does this is the critical hazard here.
Exactly. It uses these charged metal plates that operate at a really high voltage, and the process of charging those plates to attract the catalyst fines creates sparks.
Not sometimes. All the time.
All the time. Constant, predictable, frequent sparks are a normal part of its operation.
So the refinery is operating an essential piece of equipment that is, by its very nature, a permanent and known source of ignition.
Right.
Which means if flammable vapor ever reaches that ESP, ignition isn't just likely, it is 100% guaranteed. The only defense is making sure that vapor never, ever gets there.
Correct. The entire safety architecture of the FCC rests on physical barriers and pressure barriers, keeping that air side totally isolated from the hydrocarbon side.
So the countdown to disaster didn't begin on the morning of the 18th. It really began 2 days earlier, on Monday, February 16th, 2015. Walk us through that very first domino to fall.
The chain really got started when a piece of machinery on the air side called the expander began vibrating excessively.
And this expander helps drive the main air blower for the unit.
It does. And we believe the vibration was due to a buildup of catalyst particles. And these vibrations weren't minor. They were severe enough that at 12:50 p.m., the control system recognized the danger and automatically triggered an emergency standby sequence.
A sequence ExxonMobil called Safe Park.
Safe Park, yes.
It sounds reassuring, doesn't it? But based on everything the CSB found, this was actually the unit's most vulnerable state.
It absolutely was. Safe Park is essentially putting the unit in idle. It's designed to bring it safely offline without a full shutdown, holding it in this temporary state until the mechanical issue, in this case the expander vibration, can be fixed.
Okay, so what happens automatically when it goes into Safe Park?
It's critical. The hydrocarbon feed stops, the airflow stops, and two major slide valves slam shut. Those are the spent catalyst slide valve, or SCSV, and the regenerated catalyst slide valve, the RCSV. At the same time, steam is injected into the reactor riser.
But, and this is the key detail, the one piece of equipment that remains energized, that guaranteed ignition source,
Is the ESP.
the ESP is still on, still sparking away. So while the whole unit is in this critical, vulnerable standby state, ExxonMobil was relying on two primary independent safeguards to keep those two sides isolated.
That's right. The first of those was what we call the catalyst barrier.
A physical barrier.
Physical barrier. These slide valves, the SCSV and RCSV, they're massive, but they aren't designed to be perfect seals. So the design relies on the sheer weight of these catalyst particles to accumulate on top of the closed valve.
It creates a plug.
It creates a physical plug, a solid, dense, granular seal made of catalyst, and that plug is what's supposed to prevent any flow between the reactor and the regenerator.
Okay, so that's the physical barrier. Safeguard number one. What was the second?
The second was the steam barrier. This is a pressure barrier. Steam is injected into the reactor riser, and its job is to maintain a positive pressure gradient.
Meaning the pressure inside the reactor is kept just slightly higher than the pressure in the main column on the hydrocarbon side.
Exactly. So that if any minor leak were to happen, the steam would flow out towards the main column, pushing back and preventing those highly flammable hydrocarbons from ever flowing backward toward the air side.
So a solid plug and a pressure countermeasure. Simple enough, but both of those safeguards failed catastrophically. Let's start with that first point of failure, the SCSV.
This is really where the long-term mechanical integrity failure comes into sharp focus. The spent catalyst slide valve, the SCSV, it sits in an extremely abrasive surface.
You've described it before as basically getting sandblasted.
That's a perfect analogy. It's getting sandblasted 24 hours a day, 7 days a week by this flow of super hot fluidized catalyst particles.
And this particular valve had been in service for a long time.
A very long time. It had been in continuous service for over 6 years, since January of 2009.
And what was its expected life?
ExxonMobil's own internal documents suggested a predicted run length for a valve in that service was closer to 4 to 5 years, so they were already operating well beyond their own comfort zone.
And they hadn't done a comprehensive risk reassessment for that extension?
No. And the physical result of those 6+ years of constant sandblasting was severe erosion. The metal of the valve slide and its seating surfaces were just worn away.
How bad was it?
Post-incident inspection, after they took it apart, revealed that even when the control system said the valve was fully closed, there was still a gap, an open path of approximately 16 square inches.
16 square inches. I mean, to put that in perspective for you listening, that's not a pinhole. That is a massive hole. It's roughly the size of a large smartphone, a huge breach.
So it's a direct, massive bypass. And the most compelling evidence that this degradation wasn't just known, but measurable, come from comparing it to the last time they entered Safe Park.
Which was back in 2012.
Right. In 2012, when the SCSV was, still relatively functional, it took a full 20 minutes for catalyst to start leaking past that closed valve.
And that 20 minutes was enough time to form that crucial catalyst plug.
It was. But in 2015...
Different story.
Completely different story. Because of that advanced 6-year erosion that created the 16 square inch opening, the catalyst just poured through that breach in just 9 minutes.
Wow.
Within minutes of entering Safe Park on February 16th, the SCSV completely failed to hold that physical catalyst plug. Safeguard 1, the physical barrier, was gone. Just like that. A direct pathway was now open between the hydrocarbon side and the air side.
Okay, so by Monday the 16th, our primary physical barrier is toast. It's completely breached. The entire safety of the unit is now riding on that secondary safeguard, the steam barrier.
Right. And that brings us to how a completely separate, hidden mechanical problem set the stage for that pressure barrier to fail as well.
That's right. So the physical barrier was gone, but the steam barrier, it still had to overcome the pressure in the main column.
And this is where a hidden, long-running equipment failure created what you could call a pressure trap. The pressure on the hydrocarbon side in the main column was abnormally high, dangerously high.
And this wasn't even a problem inside the FCC unit itself, was it? It was an issue elsewhere in the refinery that was having this knock-on effect.
Exactly. It was a heat exchanger, specifically a standby heat exchanger on the slurry oil pump-around loop. This loop takes heat out of the system and provides it to a neighboring unit.
And the tubes inside this heat exchanger had developed leaks?
They had. And the leak was allowing light hydrocarbons, specifically naphtha, to bleed from a higher pressure system into the lower pressure slurry oil.
And slurry oil is incredibly hot.
Extremely hot, over 600 degrees Fahrenheit. So this naphtha, which is much lighter and more volatile, it hit that hot slurry oil and immediately vaporized. It flashed into a gas.
Which significantly increased the gas volume and therefore the pressure in the whole system.
Exactly. It jacked up the pressure in the main column. So instead of the typical 4 Ps of pressure they saw during the 2012 Safe Park incident, the main column was now running at 8.5 to 10 psic. Double.
So the system was already fundamentally unstable because of this hidden leak, even before any maintenance work began.
It was a ticking time bomb. You now have this high-pressure environment full of flammable gas, and the only thing keeping it from finding that 16-square-inch hole in the SCSV is the counterpressure from the injected steam.
Okay, which brings us to the final fatal management decision on the morning of Wednesday, February 18th. The maintenance crews needed to get inside that vibrating expander to inspect the damage.
Right, and to do that safely, they needed to install a blind flange to completely isolate it from the rest of the system.
And when they went to do that,
As soon as they cracked open the expander outlet flange to get ready, steam started pouring out of the opening.
which was physical, irrefutable proof for every single worker standing right there that the SCSV, their primary physical isolation device, was leaking profusely.
They knew. They could see it. The integrity of the system was visibly compromised.
That should have been a stop work moment. A giant red flag demanding a full, immediate shutdown to properly isolate the whole unit.
Logically, yes, it should have been. But management was focused on getting the maintenance work done. And the escaping steam was creating a burn hazard for the workers who were trying to install that blind.
So a decision was made.
A decision was made to reduce the steam flow to the reactor riser.
And they justified this reduction by pulling out that old, unverified 2012 variance document.
A 3-year-old document that cited a minimum safe steam flow of 2,000 pounds per hour. Based on that, they dropped the riser steam flow from about 20,000 pounds per hour all the way down to just 7,500 pounds per hour.
A tactical decision made to stop the steam from burning the maintenance crew.
Exactly.
But wait a second, 7,500 pounds per hour is still over 3 times the 2,000 pound per hour minimum they were citing. So why wasn't that safe?
Because that 2,000 pounds per hour figure was based on the operating conditions of 2012. It assumed a main column pressure of around 4 psic.
Which wasn't the case in 2015.
Not at all. In 2015, thanks to that hidden naphtha leak, the main column was running at 9 to 10 psic. So 7,500 pounds per hour of steam, while technically above that old invalid number, was simply not enough to overcome that abnormally high pressure.
So the moment they reduced the steam flow.
That was the critical moment. The pressure gradient inverted. The reactor pressure dropped below the main column pressure.
And the high-pressure hydrocarbons on the other side suddenly found the path of least resistance.
And with the physical catalyst barrier already gone because of the eroded SCSV, the deadly flow path opened fully.
Unrestricted.
Light hydrocarbons just started flowing backward from the high-pressure main column through the reactor, easily through that 16-square-inch hole in the SCSV, into the regenerator, through the entire airside flue gas system, and heading straight for the ESP.
And the timeline of that final failure is just terrifyingly quick.
It is. At 8:07 a.m., a maintenance supervisor got the first alarm on his personal hydrogen sulfide monitor, H2S. That's the telltale signature of FCC hydrocarbons, the first direct evidence of a leak.
But they didn't evacuate then.
No, they kept working. It wasn't until 8:40 a.m., a full 33 minutes later, that multiple workers started getting H2S alarms. By then, it was a massive leak.
And they finally evacuated the unit.
They did. The supervisor ordered the steam flow to be increased again, trying to reverse the problem, but it was far, far too late. The hydrocarbon mixture had already saturated the entire airside system.
And then at 8:48 a.m., it reached the ultimate ignition source.
That flammable mixture reached the ESP. It mixed with the residual air in the system, some of it being fed by CO boiler fans that were still running. It met the constant sparks from the charged plates, and it violently exploded.
That earthquake registering blast, the result of 2 days of cumulative failures, sealed by one single critical decision to reduce the final pressure barrier.
When you really dig into the CSB's findings, it's just so clear that the physical failures, the eroded valve, the pressure inversion, they were just the symptoms.
The disease was a profound systemic failure in ExxonMobil's process safety management system.
Yes. And we have to break down these managerial and procedural root causes, because these are the crucial lessons for the entire industry.
So where do we start?
We have to start with the procedural void that even allowed that final maintenance decision to happen. The CSB called it Key Lesson 5. inadequate safe park procedure.
Right. They had procedures for how to enter Safe Park and how to exit Safe Park, but nothing for what to do while you're operating in it.
Exactly. And that lack of a procedure for continuous operation in this high-hazard, non-routine state was just devastating. It meant there were no clearly defined safe operating limits.
No tripwires.
No tripwires. No established criteria that mandated if safeguard X or Y fails, you must immediately execute a full positive shutdown. And without that procedure, the operators and supervisors, they defaulted to prioritizing maintenance efficiency over verifying the integrity of their compromised barriers. They were institutionally operating completely blind.
And that procedural gap is what allowed them to ignore direct evidence of failure. Which brings us right to key lesson 1, reliance on indirect monitoring. This is where the paper trail completely failed to match reality.
In these high-hazard industries, you have to rely on direct, verifiable metrics for your safety-critical functions. ExxonMobil was relying on indirect parameters. For instance, they were looking at the SCSV valve position, just a signal in the control system that says closed to confirm the catalyst barrier was in place.
That's an assumption, not a measurement.
It's a total assumption. What they should have been monitoring directly was the differential pressure. There was a specific data point, PDC tag 4, that measures the pressure exerted by the catalyst plug above the SCSV. It's the direct physical confirmation of the plug's existence.
And what did that tag show?
In 2012, when the catalyst plug successfully formed, that tag showed a 5 psi pressure difference. In 2015, that same data tag, which was available in the control room, showed zero. Zero pressure difference, meaning the catalyst plug was gone. They had the documentation right there in the system confirming the failure of Safeguard 1, but it was being ignored because the procedure didn't tell them to look at it.
And it was the same story with the steam barrier.
The exact same story. They relied on that historical minimum flow rate of 2,000 pounds per hour instead of directly monitoring the pressure differential between the reactor and the main column. Had they done that, the control room would have seen the main column pressure creeping up towards 10 psig and known instantly that 7,500 pounds per hour of steam would never, ever be enough.
This reliance on indirect measures just robbed them of any chance to intervene early.
It did.
Now we have to talk about the astounding error of reusing a 3-year-old deviation document. Key lesson 2, management of change failure.
MOC. It is the absolute bedrock of process safety. Any change to equipment, to procedure, to operating limits, it must be formally reviewed by a multidisciplinary team.
And that decision to cut the steam flow on February 18th was based entirely on that unverified manager-approved deviation from 2012.
And reusing that deviation without a formal MOC was a total systemic breakdown. The system was broken.
Why was the 2012 variance so invalid in 2015?
Because the underlying conditions of the system had fundamentally changed on 2 major fronts. First, the SCSV erosion was drastically worse, which destroyed the physical barrier. And second, the main column pressure was abnormally high due to that hidden heat exchanger leak.
A basic MOC review would have caught that.
Instantly. An engineer, an operator, a safety professional. They would have immediately seen those 2 key differences and invalidated the 2012 procedure. But they proceeded without any review at all.
And this brings us back to that really crucial human detail that the CSB uncovered in their interviews, the operator's concern.
That moment just encapsulates the failure of their safety culture. An experienced operator actually questioned the low steam rate. He essentially asked, shouldn't it be a lot higher than that? Doesn't this feel too low given the circumstances?
And his critical judgment, born from years of experience on that unit.
It was just summarily dismissed by the supervisor. He just pointed to the engineer-approved 2012 paperwork. The system prioritized adherence to outdated, invalid paper over the real-time, empirical doubt of the person who actually had the best feel for the unit's condition.
It's a chilling example of procedure just completely trumping reality.
Huh.
Let's move to key lesson 3, mechanical integrity system failure. The SCSV was known to be a safety-critical device, yet they allowed it to deteriorate so far past its expected lifespan.
This is a classic conflict you see between maintenance economics and safety assurance. Running that SCSV for over 6 years, 2 years beyond its predicted run length, was a gamble. But even worse than just extending its life was the flawed maintenance testing strategy. They failed to test the actual safety function of the device.
Okay, explain the difference there. What's mechanical function versus safety function?
So mechanical testing just checks, did the motor move the valve? Did the control system get the closed signal? The answer was yes.
Check the box.
Check the box. But safety function testing checks. When the valve is closed, does it actually maintain a seal? Can it hold that catalyst plug under pressure? Because the SCSV was classified as a control valve, not a block valve, it was never robustly tested for its ability to act as a final isolation barrier in an emergency.
So they were relying on an eroded control valve, which is designed for throttling flow, to perform a critical sealing function that was way beyond its design capabilities.
Right. And this feeds directly into key lesson 4, which is about the gaps in their initial hazard analysis. They knew erosion was happening, but they categorized the consequence completely wrong.
How so?
Their damage mechanism review, or DMR, for the SCSV erosion, it acknowledged the wear and tear. But the review only noted the potential for financial consequences.
So that the valve might fail during normal operation and cost them money to replace.
Exactly. It completely failed to identify the catastrophic safety consequence that this erosion posed during the high-risk, non-routine operating mode of Safe Park. The entire hazard analysis was skewed toward maximizing uptime, not minimizing the risk of a massive explosion during a shutdown.
Okay, and finally, let's revisit the detection failure. The ultimate cause of the ignition was the ESP. But why didn't their safety systems detect the hydrocarbons that were flowing right toward it?
This might be the most dangerous systemic flaw because it could exist in many other refineries. Their initial process hazard analysis for the ESP actually did anticipate that flammable vapor could reach the ignition source.
So they saw the risk.
They saw the risk, but they made a massive, fatal assumption. They assumed that flammable vapor would always be accompanied by carbon monoxide, CO. They figured any leak would happen during high-temperature regeneration, which would result in partial combustion, creating CO.
So the safeguard they installed was a very expensive, custom-designed CO analyzer system.
Which was completely useless in this scenario. Because the unit was in Safe Park, the regenerator temperature had dropped way down, so the hydrocarbons entered the flue gas system cold, without any combustion.
Meaning there was no CO present.
No CO. The sole detection safeguard they had was rendered completely blind to the threat. Hydrocarbons just flowed silently and invisibly right to the spark source.
The Torrance disaster was the culmination of all these layered failures. An eroded valve, a hidden pressure leak, no procedure for Safe Park, using indirect monitoring, the MOC failure, the flawed maintenance, the bad hazard review, and a blind detection system. Each failure just reinforced the others until the system had absolutely no integrity left.
And while the systemic failures are complex, the human and environmental consequence, it cannot be overstated. We need to turn our attention to the near catastrophe that involved the modified hydrofluoric acid, or MHF alkylation unit.
This is the part of the story that is just truly terrifying. This is the moment where the accident risked escalating from a severe industrial incident into a genuine regional disaster. How close did they actually come to a mass casualty event?
Frighteningly close. The force of the explosion was so immense that a large, heavy section of debris, the CSB estimated it weighed 80,000 pounds.
80,000 pounds, that's the weight of a fully loaded semi-truck.
It was launched nearly 100 feet through the air.
100 feet.
And this massive piece of debris narrowly missed the settler tanks in the adjacent MHF alkylation unit.
And those tanks contained tens of thousands of pounds of modified hydrofluoric acid.
Yes. And if you're not familiar with HF, you need to understand that this is one of the most dangerous chemicals in industrial use.
Describe the danger of a large HF release in a place like Torrance.
MHF is highly corrosive and extremely toxic. If it's released, it vaporizes almost instantly and forms a dense, low-lying toxic cloud.
And because it's heavier than air, that cloud doesn't just dissipate.
No, it travels along the ground, engulfing everything in its path, potentially for miles. Exposure causes severe respiratory damage, horrific burns, and in sufficient concentration, asphyxiation and death. Given the massive population density around that refinery, a breach of those tanks could have been an unimaginable disaster.
The CSB chairperson at the time, Vanessa Allen Sutherland, she said it very plainly. She said the community was really, really lucky.
It was pure luck. And that brings the issue of equipment siting into sharp focus. The explosion point, the ESP, was built only about 80 feet away from those MHF settler tanks.
Now, in safety assessments, companies are supposed to analyze the risks posed by adjacent equipment. What did ExxonMobil's risk assessments say about that proximity?
This is unbelievable. Their internal risk assessments for siting hazards only analyzed potential threats within a 50-foot radius.
So because the MHF unit was 80 feet away, it was conveniently excluded from the formal analysis.
It was never formally analyzed for the risk of an external explosion from the ESP. The CSB was emphatic about this. This near miss should have been anticipated and should have been prevented by adequate siting analysis and proper isolation procedures.
And when the CSB, the federal agency responsible for investigating these accidents, tried to get information about the MHF safeguards, they hit a brick wall, didn't they?
They faced significant resistance. ExxonMobil, citing jurisdictional issues, initially refused to provide the CSB with information detailing the safeguards they had in place to prevent or mitigate a release of MHF.
The CSB had to take them to court.
They had to issue subpoenas and pursue enforcement in federal court just to get access to basic safety information. And that resistance, it just amplified the public's perception of how severe and sensitive this hazard really was.
Right. It makes everyone ask, what are you hiding?
Exactly.
So beyond that terrifying near miss, what was the tangible community and economic fallout?
For the community, the immediate impact was that catalyst dust just blanketing everything. It required immediate cleanup. It caused immense anxiety. Local authorities issued shelter-in-place advisories, which created confusion and a lot of distrust among residents.
And economically, the ripple effect was just massive.
Absolutely massive. The Torrance Refinery, it's not the biggest, but it was responsible for about 10% of California's entire gasoline supply.
10%.
And with that FCC unit disabled and the refinery running at severely limited capacity for over a year, the disruption caused huge supply constraints and price spikes across the entire state. The total cost to California drivers, directly attributable to this supply shock, was estimated at an astronomical $2.4 billion.
$2.4 billion. It just shows that these failures aren't contained to the facility fence line. They hit consumers directly in their wallets.
Without a doubt.
And the regulators, QHSE, they obviously stepped in. What was their verdict?
QHSE issued 19 citations against ExxonMobil, including 6 alleged willful violations, and sought over $500,000 in penalties.
And a willful violation is extremely serious.
It's the most serious. It means the agency alleges that company management was aware of a hazardous condition, like the defective slide valve, and yet failed to take action to correct it. It's a formal finding that this wasn't just negligence, it was a deliberate disregard for established safety rules.
And we should note, this wasn't just an isolated blip. The systemic safety issues seemed to persist even after the ownership of the refinery changed hands.
That is critical context.
Yeah.
Even after the 2015 blast, while still under ExxonMobil's control and then later under PBF Energy, the refinery had multiple other incidents. There was a small but very concerning HF leak in September 2015 and fires in 2016 and 2017.
The pattern.
It's a pattern that strongly suggests the problem wasn't just one bad valve or one management team in 2015, but a deep-seated weakness in the institutional approach to process safety, a culture that took years to truly dismantle and correct.
The Torrance explosion really is a masterclass in how these seemingly isolated technical problems, an eroded valve, a leaky heat exchanger, can converge with procedural apathy like the MOC failure and the indirect monitoring to create a catastrophe.
It is.
So what are the high-level systemic takeaways that the refining industry has to implement to prevent this from happening again?
The overarching lesson is the need for verification. We have to shift the focus from merely checking boxes on a procedure, did the valve get the close signal, to ensuring that safety-critical equipment can actually perform its required safety function in all operating modes.
Especially in high-risk, non-routine states like Safe Park.
Especially then. We have to move from just believing a procedure is safe because it's written down to having verified physical proof that the system is truly isolated and protected.
And that requires making robust MOC practices part of every single decision that deviates from the norm.
Yes. The casual, unreviewed reuse of that 2012 variance has to become unthinkable across the industry. When conditions change, and conditions are always changing in a refinery, the safety review must be mandatory and thorough.
And what about the physical isolation itself? The SCSV proved it was completely unreliable as a final barrier.
This was key lesson 7 from the CSB. The absolute necessity of adopting positive isolation methods instead of relying on control valves like the SCSV.
Explain that. Positive isolation.
Think of it this way. Your SCSV is like the spring latch on a screen door. It might click shut, but you would never rely on it to keep a burglar out. Positive isolation, using methods like installing a blind flange or a double block and bleed system, that's the deadbolt. It physically and verifiably separates the hazardous energy sources, and that has to be the standard for safety-critical maintenance.
Now, the CSB recognized that some of these failures, particularly that hydrocarbon detection flaw, might be industry-wide blind spots. What did they recommend to the American fuel and petrochemical manufacturers, the AFPM?
They called for collective industry action. They wanted them to share this institutional knowledge. Specifically, they recommended that AFPM hold forums to spread the lessons on preventing ESP explosions.
Focusing on two key areas.
Two key areas. First, developing reliable methods for the detection of cold hydrocarbons in flue gas systems to address that CO analyzer flaw. And second, improving positive isolation strategies during these non-routine standby modes. That detection failure was a critical gap that the entire sector needed to fix together.
In this incident, it clearly had a major impact on regulatory policy here in California. How did Torrance spur regulatory reform?
Torrance was a huge catalyst. California started developing new process safety management regulations that significantly raised the bar for oversight and analysis. They're requiring 3 major enhancements that directly target the weaknesses we saw at ExxonMobil.
The first one is expanding the scope of those damage mechanism reviews, the DMRs.
Yes. The new rules require DMRs to specifically consider the consequences of equipment degradation during non-routine operations. This forces companies to analyze things like SCSV erosion not just as a financial risk, but as a critical safety risk during a mode like Safe Park.
And second, the state is mandating increased employee participation.
This is so crucial for fixing that culture issue. It mandates the formal integration of experienced frontline operators and maintenance workers into safety analyses, the PHAs and MOCs at the earliest stages.
It institutionalizes the operator's concern.
It does. It means that when an experienced person raises a doubt about a low steam rate, the system has to stop and formally address it, rather than just dismissing it with outdated paperwork.
And finally, they're requiring something called Safeguard Protection Analysis, or LPA.
Right. LPA stands for Layers of Protection Analysis. This requires a rigorous, structured, semi-quantitative study to assess the effectiveness and availability of your critical safety barriers. Companies can no longer just assume the SCSV will hold a catalyst plug.
They have to prove it.
They have to calculate the probability of failure and confirm that their safeguards are truly independent and robust enough to handle the risks. It essentially forces companies to rigorously audit their own layers of protection, ensuring their defenses are real, not just theoretical lines on a diagram.
The ExxonMobil Torrance explosion of 2015 really is a defining event in the history of process safety. It wasn't a freak accident. It was the predictable outcome of layers of mechanical degradation and procedural shortcuts.
Wow.
A chain that started with an eroded valve and ended with a violent explosion and an astonishing near miss aimed straight at a densely populated community.
The sheer cost of that systemic failure is just staggering. Not just the $2.4 billion loss to California consumers or the injuries to workers, but the near total loss of public trust. It's a painful reminder that in these high-hazard environments, safety management has to be dynamic, it has to be verified, and it has to be continuously challenged.
We've traced the entire chain of events today, from the 6 years of SCSV erosion and that hidden naphtha leak, to the fatal decision to cut the steam flow based on an outdated memo, and the failure of safety equipment to detect a cold hydrocarbon leak. It all begs the question we started with. If safety is truly paramount, why do large corporations so frequently choose to extend the lifespan of safety-critical equipment beyond its recommended limits? And why are procedural shortcuts, like reusing an unverified variance, so easily prioritized over the unwavering commitment required for verifiable, positive isolation?
You know, the inherent tension between maximizing production, minimizing downtime, and ensuring comprehensive safety is a constant negotiation in this industry. I think the crucial lesson from Torrance is that when companies choose to gamble on the lifespan of a single valve or ignore the need for a proper MOC, it's the public that ultimately pays the price, both in dollars and in narrowly averted disaster. The system has to be designed so that safety isn't merely a preference, but an inescapable requirement.
Something powerful for you to consider as regulatory bodies continue to refine these standards.